Hello and welcome to the third part of our first lesson in our fifth unit, Sine Functions, in our grade 11 University College math class. So we've been introduced to angles of rotation, both positive and negative. We've learned how to create coterminal angles, and now we're going to see how does that all connect to what we're doing with the sine ratio, or this, I guess we're doing the sine functions broadly. And it all starts with this idea of a unit circle, and it ties into this idea behind coterminal angles. So let's start by looking at a unit circle, and the unit circle is right here. Now a unit circle is basically a circle where the distance from the center to any point along the circumference has a length of 1. So basically this radius here is going to have a length of 1 all the way around, and it would be true here or here or here, basically anywhere around this circle. That's why we call it a unit circle, is because it has 1 unit as its radius. Now if we were going to inscribe, which means to sort of draw inside, if we were going to inscribe a triangle into this unit circle at any point sort of along the way, again I've just created one here, but we could just as easily have made a triangle over here or a triangle down here. And if we, once we've created this triangle, we were to label it from this angle of rotation, and we are looking for the opposite hypotenuse and adjacent sides, very much like we did it in the trig unit. So if we were to do that, our side little y would be our opposite, our side little r would be our hypotenuse. This is sort of a right angle right there, and the side little x is our adjacent. So if we wanted to create the sine ratio from primary trig ratios from within this triangle, this inscribed triangle, we would end up with the sine of angle theta, which is our angle of rotation, is equal to the opposite over the hypotenuse. And using the letters provided in this particular question, we have the sine of theta is equal to y over r. Now, because this is a unit circle, we know that, I'm just going to change up my colors here, since we know that r is equal to 1, which makes this true of a unit circle, therefore the actual sine ratio is the sine of angle theta is equal to y over 1, or I'm just going to call it y. So why is this important? It's important because what it's saying is the sine of any angle of rotation is equal to the y value, which is the height. If we look back at our triangle here, it represents the height of our function above or relative to the x-axis, which is kind of, you could imagine it running through here. If we were to draw another triangle over here, there's our righty, this would be the y value here. That would be its height. If we were to do another triangle sort of down here, oh, that was not right, down here, we would have this as our y value, so you can see how the y values would be both positive or negative. So what can we do with this? Well, what we can do is we can map out how this particular function is going to change as it rotates 360 degrees. So as our terminal arm rotates around this entire circle and comes back to where it started, we can actually explore what the output values are. So given that y is equal to sine of 0, what I'm going to type into my calculator is sine 0 equals, and it's going to equal 0. So I'm going to pop that in there right there. That means, and that makes sense for us, because if you can imagine, we're talking about it right here. It has a height of 0. It's literally sitting right on the x-axis. Let's try some of these other values. So I'm just typing these into my calculator. The sine of 30 degrees is equal to 0.5. The sine of 60 degrees is equal to 0.87. The sine of 90 degrees is equal to 1. And again, that makes sense, right? We can sort of look back at our triangle. We can see that the sine of 90 degrees, which is this height right here, it's actually just a radius at that point. So it makes sense that it has a height of 1. Let's just continue on. So sine of 120 degrees, 0.87. Sine of 150 degrees, 0.5. Sine of 180 degrees is 0. And again, that makes sense. If we look over here at 180 degrees, the height of our triangle is like literally sitting right on the x-axis, so it would have a height of 0. That makes sense. The sine of 210 degrees is negative 0.5. The sine of 240 degrees is equal to negative 0.87. The sine of 270 is equal to negative 1. Sine of 300, negative 0.87. The sine of 330 is negative 0.5. And the sine of 360 is 0. So I made all these calculations. What we've seen is that as we make our way around the triangle, we have locked down particular heights. And these heights have a pattern. So the pattern is, and I've written it down here, in the first quadrant. So if you can imagine this first quadrant, which I'm going to change up my colors here and sort of clean up our graph a little bit. The first quadrant over here, quadrant number 1 is right here. This is quadrant 1, and we can see that the path of our y values are increasing. Makes sense. In quadrant 2, we can see that the values of our y are decreasing to 0, but are still positive. Then from 180 to 270, we can see that our y values, our output values, are getting more negative. And then heading from 270 up to 360, it's still negative, but now it's increasing again. So I've articulated that in this table down here, where we are positive in the first quadrant, positive in the second quadrant, negative in the third quadrant, and negative in the fourth quadrant. So how does this look? If you can imagine making this graph, how does it look? I'm a little bit lazy, so I didn't actually just sketch this. I left it in from the completed notes. So here would be a good time to pause your video and just sketch the points on. I'll give you a moment to do that. So hit pause. I'm really just sketching in the numbers from that table of values that we created right up here. So this table of values, that's what I'm graphing. So take a moment, pause the video here, and just fill this in. When you're done, come on back and we'll just talk a little bit about what makes makes this unique. Okay, so you're back. We call this this particular configuration of points a wave. It has a wave look about it. And the other thing that we notice about it is I've drawn in little arrows here on the ends. And the reason I've drawn in these little arrows is that you can imagine if we were to continue rotating in a negative direction, this graph would then continue down off in this direction. And if we were to continue past 360 degrees, so 370, 380, etc., this thing would continue to head back up towards 1. So this graph is going to continue on in both directions forever and ever. So we call this a sine wave. We define this as a periodic function, which means that at a certain point it starts repeating itself. And the point at which it starts repeating itself in this case is 360 degrees. Then we're going to see that pattern start up again, which is again where coterminal angles comes in, because we know that at both 0 and 360 our function sine of theta has an output of 0. That's the same value twice for two different angles of rotation. This will go on more and more and more out forever in both directions. So let's just tie this back to unit 1. Is this above curve a function? The answer is yes. And it is a function because it passes the vertical line test, which, if you don't remember, if we were to draw vertical line test, if we were to draw vertical lines through this, let me just change up my color scheme here. If I draw vertical lines through this function, it hits once and only once. It's never hitting more than once, which makes this thing a function. So that is the end of our first lesson in Unit 5. Tackle a little bit of this homework, see that it makes sense. Go watch some of the videos again in this lesson if you aren't 100% sure what's going on. And I'll see you back here for lesson number 2.